So, hey everybody, today we're going to see the Unit 1 analysis of algorithms. So, let's start and jump into the introduction. A common person's belief is that a computer can do anything. This is far from truth. In reality, computer can perform only certain predefined instructions. The formal representation of this model as a sequence of instructions is called an algorithm. and and coded algorithm in a specific computer language is called a program. Analysis of algorithms can be an area of research in computer science. Evolution of very high speed computers has not diluted the need for the design of time efficient algorithms. Complexity theory in computer science is a part of theory of computation dealing with the resources required during computation to solve a given problem. The most common resources are time. How many steps time does it take to solve a problem? And space. How much memory does it take to solve a problem? It may be noted that complexity theory differs from computability theory, which deals with whether a problem can be solved or not through algorithms, regardless of the resources required. Analysis of algorithms is a field of computer science whose overall goal is understand the complexity of algorithms. While an extremely large amount of research work is devoted to the worst case evaluations, the focus in these pages is methods for average case. One can easily grasp that the focus has shifted from computer to computer programming and then to creation of an algorithm. This is algorithm design, heart of problem solving. Objectives. After going through this unit, you should be able to understand the concept of algorithm, understand the mathematical foundation underlying the analysis of algorithm, to understand various asymptotic notations such as big O notation, theta notation, and omega. Here you can see big O, uh, theta, and omega for analysis of algorithms. Understand various notations for defining the complexity of algorithm. Define the complexity of various well-known algorithms and learn the method to calculate time complexity of algorithm. Mathematical background. To analyze an algorithm is to determine the amount of resources such as time and storage that are utilized by to execute. Most algorithms are designed to work with inputs of arbitrary length. Algorithm analysis is an important part of a broader computational complexity theory, which provides theoretical estimates for the resources needed by any algorithm which solves a given computational problem. These estimates provide an insight into reasonable directions of search for efficient algorithms. Definition of algorithm. Algorithm should have the following five characteristic features: input, output, definiteness, effectiveness, termination. Therefore, an algorithm can be defined as a sequence of definite and effective instructions which terminates with the production of correct output from the given input. Complexity classes. All decision problems fall into sets of comparable complexity called complexity classes. The complexity class P is the set of decision problems that can be solved by a deterministic machine in polynomial time. This class corresponds to set of problems which can be effectively solved in the worst cases. We will consider algorithms belonging to this class for analysis of time complexity. Not all algorithms in these classes make practical sense as many of them have higher complexity. These are discussed later. The complexity class NP is a set of decision problems that can be solved by a non-deterministic machine in polynomial time. This class contains many problems like Boolean satisfiability problem, Ha- Hamiltonian path problem, and the vertex cover problem. What is complexity? Complexity refers to the rate at which the required storage or consumed time grows as a function of the problem size. The absolute growth depends on the machine used to execute the program, the compiler used to construct the program, and many other factors. We would like to have a way of describing the inherent complexity of a program or piece of a program independent of machine/compiler considerations. This means that we must not try to describe the absolute time or storage needed. We must instead concentrate on a proportionality approach, expressing the complexity in terms of its relationship to some known function. This type of analysis is known as asymptotic analysis. It may be noted that we are dealing with complexity of an algorithm, not that of a problem. For example, the simple problem could have high order of time complexity and vice versa. Asymptotic analysis is based on the idea that as the problem size grows, the complexity can be described as a simple proportionality to some known function. This idea is incorporated in the big O, omega, and theta notation for asymptotic performance. The notations like little o are similar in spirit to big O, but are rarely used in computer science for asymptotic analysis. Trade-off between space and time complexity. We may sometimes seek a trade-off between space and time complexity. For example, we may have to choose a data structure that requires a lot of storage in order to reduce the computation time. Therefore, the programmer must make a judicious choice from an informed point of view. The programmer must have some verifiable basis based on which a data structure or algorithm can be selected. Complexity analysis provides such a basis. We will learn about various techniques to bind the complexity function. In fact, our aim is not to count the exact number of steps of a program or the exact amount of time required for executing an algorithm. In theoretical analysis of algorithms, it is common to estimate their complexity in asymptotic sense. That is to estimate the complexity function for reasonably large length of input n. Big O notation, omega notation, and theta notation are used for this purpose in order to measure the performance of an algorithm underlying the computer program. Our approach would be based on a concept called asymptotic measure of complexity of algorithm. There are notations like big O, big theta, big omega for big O omega theta omega for asymptotic measure of growth functions of algorithms, the most common being big O notation. The asymptotic analysis of algorithms is often used because time taken to execute an algorithm varies with the input n and other factors which may differ from computer to computer and from run to run. The essences of these asymptotic notations are to bind the growth function of time complexity with a function for sufficiently large input. The theta notation, tide bound. This notation bounds a function to within constant factors. We say Fn is equal to theta Gn if there exist positive constants n, O, C1 and C2 such that to the right of NO the value of Fn always lies between C1Gn and C2Gn, both inclusive. The figure 1.1 gives an idea about function Fn and Gn where Fn is equal to theta Gn. We will say that the function Gn is asymptotically tight bound for Fn. Now comes for example, let us show that the function Fn is equal to 1 by 3n square minus 4n is equal to theta n square. Now we have to find three positive constants c1, c2 and no such that c1 n square is less than equal to 1 by 3n square minus 4n less than equal to c square n square. For all n is equal to greater than equal to no, which implies c1 is less than equal to 1 by 3 minus 4 by n less than equal to c by c2. By choosing no is equal to 1 and c2 greater than equal to 1 by 3, the right hand inequality holds true. Similarly, by selecting no is equal to 13, c1 is less than equal to 1 by 39, right hand inequality holds true. So for c1 is equal to 1 by 39, c2 is equal to 1 by 3 and no is greater than equal to 13, it follows the 1 by 3 n square minus 4n is equal to 3 times square. Certainly there are other choices for c1, c2 and no. Now we may show that the function fn is equal to 6n cube is not equal to theta n square. To prove this, let us assume that C3 and NO exist such that 6n to the power 6n cube is less than equal to C3 n square for n is greater than equal to n, but this fails for sufficiently large n. Therefore 6n to the power 3 is not equal to theta n square. The big O notation upper bound. This notation gives an upper bound for a function to within a constant factor. Figure 1.2 shows the plot of fn is equal to 0 gn based on big O notation. We write fn is equal to 0 gn if there are positive constants no and c such that to the right of no the value of fn always lies on or below cgn. So here you can see the diagram, and yeah, you can see here. Now comes the mathematically for a given function gn, we denote a set of functions by big O gn by the following notation. Big O gn is equal to curly braces open f, and there exists a positive constant c and no such that big O is less than equal to f n less than c less than equal to cgn, and for all n is greater than equal to no. Clearly we use big O notation to define the upper bound on the function by using a constant factor c. We can see from the earlier definition of theta that theta is a tighter notation than big O notation. Fn is equal to n plus c is big O. N is also big O n square, but O n is asymptotically tight, whereas big O n square is notation. Whereas in terms of big theta notation, the above function fn is theta n. As big O notation is upper bound of function, it is often used to describe the worst case running time of algorithms. The big omega notation is lower bound. This you can see here, the graph. Okay. it's uh, it's important, so you can just see this. Yeah, the notation gives a lower bound for a function to within a constant factor. We write fn is equal to omega g n if there are positive constant n o and c such that to the right of n o the value of fn always lies on or above cg, and figure 1.3 depicts this. Yeah, figure 1.3 plot of fn omega gn. Okay, now the plot of depict the plot of fn omega gn is equal to omega gn. Mathematically, for a given function gn, we may define omega big omega gn as the set of functions omega gn is equal to fn. There exists a constant cn and o is greater than equal to o such that o is less than equal to cgn is less than equal to fn for all n is greater than no. Since omega notation describes lower bound, it is used to bound the best case running time of an algorithm. Asymptotic notation. Let us define a few functions in terms of above asymptotic notation. Example, fn is equal to 3n cube plus 2n square plus 4n plus 3. 3n cube plus 2n square plus big O n as 4 n plus 3 is of big O n. 3n cube plus big O n square as 2n square plus O n is O n square O n cube. Example, fn is equal to n square plus 3n plus 4 is 0. Big O n square, since n square plus 3n plus 4 is less than 2n square for all n is greater than 10. By definition of big O, 3n plus 4 is also big O n square 2, but as a convention we use the tighter bound of the function, that is big O n. Here are some rules about big O notation. Fn is equal to O Fn for any function f. In other words, every function is bounded by itself. A k n k n to the power k plus a k minus 1 n to the power k minus 1 plus to a1 n plus a0 is equal to big O n to the power k for all k is less than equal to greater than equal to 0, and for all a0 a1 till ak is r. In other words, every polynomial of degree k can be bounded by the function n to the power k. Smaller order terms can be ignored in big minus O notation. Big O notation. 3. Basis of logarithm can be ignored in big O notation, that is log O n is equal to O log z O log b n for any basis a b. We generally write O log n to denote a logarithm n to any base. Any logarithmic function can be bounded by a polynomial, that is log bn is equal to big O n to the power c for any b base of logarithm and any positive exponent c is greater than 0. Any polynomial function can be bounded by an exponential function, that is n to the power k is equal to big O bn b to the power n. Any exponential function can be bound by the factorial function. For example, a to the power n is equal to O is not n for any base a. So here we come to the check your progress one. If you want, you can solve for yourself, but soon answers will be there in the description. Okay, now process of analysis is there, and yeah, it's how much long? 4 pages. Okay, we will try to complete this. Okay, in the next lecture. So thank you till then and keep exploring.